So as you know, we will be recording this. This is just did, and we will put it up as a transcription, not transcription, but slightly edited if necessary on our website. So with that, now we can turn over to you, Gordon, to begin your presentation.
All right, thank you, Peter, for that introduction. So I was asked to comment on the concept of the fourth industrial revolution, which comes from a guy named Klaus Schwab of the World Economic Forum. He's actually an economist, so I have to forgive him for not knowing much history, because there's a long history of industrial revolutions. Archaeologists distinguish the Stone Age, the Chalcolithic, which is the Copper Stone Age, the Bronze Age, and the Iron Age. And each of those introduced a new military technology that destabilized the existing political order and destroyed great empires. For example, the advent of the Iron Age destroyed the Hittite Empire, which in turn led to collapse of law and order all over the Mediterranean, and almost led to the end of Egypt, but Egypt managed to survive. However, in general, on top of that, the concept of industrial revolution is a shallow concept. All new technologies are technologies. If you look at, for example, the Stone Age, the Copper Stone Age, Bronze Age, and Iron Age, copper has a lower melting point than bronze. Bronze has a lower melting point than iron, and each of them built on the pyrotechnology, the previous generation, and improved it so that they were able to go ahead with new materials that they couldn't use before. Okay, so we find that with computers as well, right? I mean, modern computers started with unit record equipment, with process and so on, and then computers took a different approach. Okay, so let's move on from there. And as Peter indicated, I'm not going to talk about artificial intelligence. So there was an industrial revolution that never happened. And what that shows you is industrial revolutions are not just technological in nature, they're social. The Roman Empire had a lot going for it, economically speaking, had mass production, Arito ware and terra sigillata pottery were made in Italy and shipped all over the empire. Also bricks that were made in various factories and shipped all over. Interchangeable parts. Catapults, Roman catapults had interchangeable parts, right? People tend to, if you ask them when interchangeable parts were introduced, they say, oh, it was guns in the 18th century. No, the Romans had interchangeable parts for their catapults. They used metal springs that were interchangeable. The Romans had trade over a large area, which required them to establish roads, although the roads were established for military reasons. But they became useful for commercial purposes, and patrols against pirates, which were important because it was very dangerous sending stuff by ship when you had pirates all over the place. So the Romans encouraged trade, and there was a vast increase in long-distance trade during the Roman Empire. They had a trade bloc with a large population. The population of the Roman Empire was 60 to 100 million people, okay? And there were no internal trade barriers, except there were harbor fees at different ports. You had to pay a tax, but it usually wasn't very much. It was usually something like 9% of the value of the cargo. And they had standard units, right? They had Roman units, for example, the mile, which is a Roman unit. It's 2,000 Roman paces. Okay, so they had a lot going for it. They had two official languages, Latin and Koine Greek. They had a single currency, it was sesterce. They had banking and finance, right? They had quite sophisticated banking and finance institutions, because that stuff was invented in Athens in the 6th and 5th centuries BC. So the Romans inherited all that. And they had insurance, at least for ships, and insurance fraud too, because we know some cases of insurance fraud. Yet they never achieved what we would recognize as an industrial revolution. why did they fail to undergo an industrial revolution? So various historians have different ideas about that. But I don't agree with any of them. They think slavery was the reason. That doesn't seem to be the reason. Free labor and slave labor competed throughout the duration of the Roman Empire. And slavery wasn't a dead end for Romans. You could buy your way out of slavery if you could earn enough money. So slavery wasn't a dead end for Romans. So I don't agree that it was the problem. Reluctance to innovate. Well, actually, the Romans mostly encouraged innovation. For example, they published manuals for agriculture and other subjects. By the end of the Western Empire, they had increased farm productivity enough to double the share of urban population from 10% to 20%. They liked increasing the urban share of population because they could tax people in cities. It wasn't practical to tax in the countryside. Most of the people didn't deal in coinage. And if you took their seed corn, they'd die. They just starved to death. So you couldn't really tax them. So the Romans encouraged urbanization, and they increased urbanization from 10% to 20%. By the way, there's a general rule there in history. People are reluctant to adopt most foreign elements of culture, but they love foreign technology, right? They're not sentimental about technology usually. There are very few technologies that really people are sentimental about. Steam trains are one. But generally people don't get sentimental about technology. They want the newest stuff because it's easier and easier to use. So I think the original question, why didn't the Romans have an industrial revolution, is based upon a false presupposition. It assumes an industrial revolution happens when then, I forgot to mention in there that the Romans they weren't only using muscle power, they had a lot of water wheels. That was discovered by my old teacher of ancient science and technology, Trevor Hodge at Carleton University. So there's a false presupposition there. It assumes that an industrial revolution happens when a new technology comes along, but ignores the many supporting technologies required by the new technology. What Schwab calls IR1, the 18th to 19th century industrial revolution, was not a self-contained event. It was the culmination of the work done by previous eras, previous generations in developing new technology and new ways of doing things. Okay, so in my view, we're still in the midst of the most important industrial revolution of all, one that took us from slavery, that's to Neolithic, which is post-agriculture, roughly 10,000 years ago in ancient Sumer, fixed location agriculture and food, right? If you're storing food, you're storing wealth. If you're storing wealth, people are going to come and steal from you. So agriculture led to living in walled fortresses, which they called cities, right? The word civilization means cities. But large communities also enabled development of more specialized technical trades, which led to technical innovation and economic growth. At the village level, you had a blacksmith, a village blacksmith. And probably was also the tinsmith and coppersmith. But that was it. It wasn't like a big city where you had jewelers and goldsmiths and all kinds of people. Anyway, so larger communications led to technical innovation and economic growth, which led to the need to keep records, which led to arithmetic and writing. And writing was the first quantized, hence digital system of data recording. In other words, when you write a symbol, it's a symbol. It can't be, this could be a letter A or it could be a letter B, but there's nothing halfway in between an A and a B. So the symbol has to have been one or the other. It can't be both or halfway in between. It can't be A and a half. There's no such symbol, right? And that's digital. So if you look at the origin of writing systems in Europe, they're all descended from Sumerian cuneiform. That's pretty old. This is a contract the picture here is showing a contract from the sale of a house and some land from about 2600 BC, at which time cuneiform was about 900 years old. I say only about 900 years old because the tablet itself is around 4600 years old. The circular and semicircular indentations represent numbers. I don't know if I can show a cursor here, but in the top right of the tablet, there are a series of circular indentations. There's some semicircular ones here. Those represent numbers. So weird. It's because they had to use clay as the writing material, and you can't use a pen in clay. You can't make a line in clay. You have to use a stylus and push it in. So they had a stylus that had kind of a triangular, one triangular end, and the other end was more circular. And so they drew symbols using that. So it's a pretty awkward system to use. But that's because of the material, which was clay. The Sumerians lived in the valley of the Tigris and Euphrates rivers, and they have descendants called Marsh Arabs who still live there today. Oh, I found a picture of a Marsh Arab the other day, but I forgot to incorporate it in this. Anyway, they're still around. There's still a few Marsh Arabs. So they're survivors of the original culture, which is a swamp culture, right? They lived in a swamp, like Dilbert Sylvanians. Anyway, what happened is they wanted to make contracts, they wanted to record transactions. So they made three-dimensional tokens to represent numbers, right? So they had like a cylinder or a cube or stuff like that, and or a sphere, and each of them represented a certain value, a numeric value. And so they started off just putting them inside clay envelopes. So the tokens were inside the envelope, and then they wanted to be able to see what was inside the envelope without breaking the envelope. So they started pressing them into the outside of the envelope. And within about 50 years, they realized, well, we don't need to put the tokens in this stupid thing. We can just keep the envelope as a contract. It's good enough. So they had, by that time, they had everything. They had recording of signatures because they had what were called cylinder seals that you could roll on the clay. And they had everything they needed for what amounts to digital storage. Okay, and that's why we can still read them today. That's why even when they're copied generation after generation, we still have something meaningful. Okay, so let's talk about computing. They wanted to record numbers, so they had to figure out how to compute numbers. Now, we don't use the Sumerian system at all, right? The Sumerians used base 60, and we don't use base 60 except for clocks. That's the only remaining, and angles. Those are the only remaining traces of Sumerian usage. What we do is we use a decimal number system, but what I want to show you here is a device that the Romans used, and it's called an abacus. The Romans did use the abacus. It wasn't a Roman invention. It was an invention of the Etruscans. The Etruscans lived in what's now called Tuscany, right? So it's really Etruscans or Tuscans. And they had a numbering system that the Romans adopted. So the Romans had these weird symbols, which are in between the two sets of beads. And you'll notice they're not the same as what you were taught in school as Roman numerals, because the modern system of Roman numerals is considerably simplified. Okay, so the Romans used the Etruscan system, and part of that was that they used the abacus. Now, the name abacus probably, it's certainly not Roman, it's probably not Etruscan either. It's probably Arabic. So it's probably somebody in the Middle East who invented the abacus. But the Romans, were prone to picking up technologies that worked for them. And so they did that. This, by the way, is an extremely rare example of a technology that started in the West and went to the East.
Mhm.
You should realize that in antiquity, the Chinese were the big innovators for almost everything because they had the largest population base and the largest economic unit. So most technologies originated in Asia, and that includes iron and includes bronze. It's only later that stuff started to happen in the West. In fact, really only two technologies originated in Europe. One of them is the abacus, and the other one, well, except as I said, it probably came from the Middle East, but it spread from the West to the East. And the other example of a Western technology that made a small difference in history was the gun, which was invented in Europe and led to centuries of European hegemony over the world, which we're finally seeing an end to. Okay, so this, so a Roman businessman, a Roman merchant carried that to India. And then the Chinese, the Indians passed it on to the Chinese, and the Chinese improved it by drilling holes in wooden beads, right? So that instead of having to pick up beads individually, like we see here, it looks, they had to actually pick up those beads and put them down. They had a little bag full of beads, and they had to pick them up and put them down. But the Chinese improved it, so you just slide the bead along on a wire or a rod. And then the Japanese made another improvement. They replaced sets of 5 beads and 2 beads with 4 and 1, which takes more skill to use, but it's faster. I would note that the museum that put these beads on the hand abacus botched them because it's only got 4 and 1, and it should be 5 and 2. Anyway, that's Chinese style abacus. No, that's a Japanese one. Sorry, because it's 4 and 1. No, it's 5. Okay, odd. Okay, so that's how computing was done in antiquity. Now, what about mechanical calculations? You might think mechanical calculators were fairly new, but they're not. The Antiquity machine, it's called Antiquity, and it was found near one of them. It was underwater. It was discovered in, I think it was 1906 or thereabouts. But it was actually a wreck from the 1st century AD. And the above image is a reconstruction because the original is a mess. It's bronze, it's all corroded together, and you can't see very much looking at it. So this is reconstructed using the latest technology, confocal X-ray scanning, in order to figure out all the gear ratios and correctly deduce what the actual mechanism was. And what it does is astrological calculations, right? So you turn it, there was a crank that you could turn. I think it's showing there on the right-hand side. So a crank on the side of the box that you could turn, and it would advance the dials by 1 day. So you could, if you knew what date it was set to, you could set it to another date by cranking it once for each day. And if you're the assistant and you accidentally crank it off by 1 day, you're really in trouble. But anyway, okay, so they could do calculations using gears, and I should point out that all these gears were handmade, right? They didn't have modern machine tools, so they couldn't make really precise gears or really precise machines of any kind. Modern machine tools only started in the 18th century and didn't become prevalent until the 19th century. So, we have a degree of precision in manufacturing stuff that they didn't have. But they did surprisingly well. The calculations, by the way, were done using the Ptolemaic system. Ptolemy was I'm not sure you'd call him an astronomer. He did some astronomy, but he was more of a theoretician, trying to describe how the solar system worked. And he came up with this system that is surprisingly accurate. It's completely non-representative, it's non-physical. But he said himself in his own book that he didn't think it was really physical, but it seemed to work. And it does give accurate answers, you know. So we shouldn't complain about it. Okay, so modern computing, well, we get to the 17th century, and Blaise Pascal, famous mathematician, his father had a contract for collecting taxes. And he came up with a mechanical geared calculator for tax calculations. This is, I believe, a reproduction. I don't think it's the original. But it is in a museum. And then we get to the 19th century, and there was a contract awarded by the British Admiralty to a guy named Charles Babbage. And this is a picture of the machine he built. It's called the difference engine. And what it does is it solves a particular set of equations, which, by the way, were developed essentially using calculus. The set of equations is, I mean, it's integrating over the curve as a shot rises and then falls due to Earth's gravity. So that's what that's what the tables are for. And this thing actually produced a printed output. Actually, each turn of the crank, it generated one more number and it printed it. So there you have a complete computer, if you will. It's not a general purpose computer. It could be, in the sense that if you put different numbers in to the difference engine, you could compute a different curve, right? It's a general algorithm. He also built portions of the analytical engine, which would have been fully functional. And I don't have a picture because he never finished it. His programmer, Ada Lovelace, Countess Ada of Lovelace, wrote that so he got her involved as programmer, and she observed that it could be used to manipulate symbols as well as to perform computations. So she was quite aware of how powerful it was. But unfortunately, Babbage, like I say, never finished it. He kept tinkering with it and never finished it. So so we didn't get mechanical steam-powered computers when we might have. Too bad. By the 1930s, there were lots of electromechanical programmable calculators, right? People started combining electrical with mechanical. Automated calculation was, as we historians say, in the air. People were working on it. There was an American professor at Tanasoff, and his graduate student Barry demonstrated all electronic calculation using a binary arithmetic unit, using vacuum tubes. Okay, this was it was shown around, and it was quite influential. Later, it influenced the American ENIAC. Meanwhile, not meanwhile, but shortly after that, World War II, a decade later, at Bletchley Park in Britain, a team that notably included Alan Turing used electronic calculation for breaking each new German Enigma code setting. Now, they at first used machines that had been thought to be, until recently, were thought to have been totally theoretical, Turing machines. But they did actually build Turing machines. However, they ended up building something much better. They developed Whirlwind. This had all electronic calculation, and it had a B register, which could be used for indirect addressing. So it was really quite sophisticated. Unfortunately. So Whirlwind was a proper computer. It had features that otherwise were not brought in to the computer business until 1950s, even maybe even the 60s. But unfortunately, it was classified top secret. So we didn't get the benefit of its architectural advances. So what you have is a machine that was too far ahead of its time for its own good, or for the good of the rest of us. Anyway, so in the 1950s, transistors made the computer much more practical. The PDP-5 that I encountered at high school was made using discrete transistors. In fact, each gate had transistors, resistors, diodes, and capacitors. So a gate was a module about 5 inches wide and about 10 inches long, something like that. Well, they could put 2 gates on that one module. So there we are. You know, that just shows how easy it is. Integrated circuits came out in the 1960s. And that started a learning curve called Moore's Law, which is gone today. It's finished. Around 2010, Moore's Law stopped working. But until then, the integrated circuits kept getting faster and smaller and using lower power. Today's integrated circuits have 4 nanometer features, and next generation specters have about 2 nanometer features. If you think that's not that small, consider that it's only about 10 atoms wide, right? In other words, we're close to physical limits. And in fact, now the dominant factor in integrated circuits is the speed of light delay carrying signals between gates, right? It's no longer so making the visual gates faster no longer gets us any increase in speed. But it does cram more circuitry on a chip. So we're still, you know, getting bigger computers, but we're not getting faster computers. So, okay. I should have made a slide about computer architectures. Specifically back in around 1980, the concept of reduced instruction set computing was introduced. And it was supposed to be based on rational design. And the idea was, if we have fewer instructions, we can make them each individually faster because we use more transistors per instruction, which made sense at the time. It doesn't make sense anymore. And people still use RISC designs. And I think they're wrong to do that, because we're past the point where that's an optimization. We're now fighting, it's like we're back in the 50s and we're fighting to get faster computers. We shouldn't be fighting to get faster instruction times. We should be fighting to put more in each instruction and take advantage of the parallelism of hardware to make the overall program go faster, because it needs fewer instructions. However, FSN nowadays is putting multiple cores on each chip. Server software has been modified to use multiple threads. That's I lived through that. I once worked on a project where you know, there was a bug that involved a race condition between threads, and people couldn't figure it out, and I could because I had a hardware background. But those days are past. Everybody knows how to do multiple threads now. It's pretty much standardized. And I mean, even ordinary smartphones use a chip from Broadcom that has 7 cores, right? So we're using multiple cores all over the damn place. Furthermore, about 2/3 of the world is currently on the internet. I got this graph last year or so. It only went up to 2021, but it does show you that we were in 2021, we were already up to 4.66 billion people on the internet, and we're not doing so badly as far as that goes, getting people onto the internet. As I said, all technologies dependent are dependent on other technologies. Optical fibers are the long distance workhorse, but there are alternatives. The Starlink satellite network, which has only gone up pretty recently and isn't finished yet. It does demonstrate there's still a need and a use for RF communications. Right? And by the way, I don't know if you're aware of this, but Starlink is going to communicate directly between their 15,000 satellites and ordinary cell phones on the ground. SpaceX have already applied for permits. Okay, so that's a second generation satellite, which is quite a bit bigger, but it's still not huge. Anyway, so we're in the realm of we've become dependent on the internet, right? We can't do business without the internet. I mean, what are we going to do? Are we going to cut Russia off the internet? Not going to happen. We can't afford to. Anyway, so near-term computer advances, there will be advances over the next 5 years. Moore's law is dead, so we're not going to keep getting faster and faster CPUs. In fact, the fastest Intel CPUs have been 4 gigahertz for quite a while now. And IBM is all proud of itself because they have 5 gigahertz CPUs in their PowerPC series, but they're really pushing it to get that. However, here's a few oddball things. Now, I'm not in on anybody's hardware planning. I'm not relying on any internal information here. So these are just speculative on my part. I expect further improvements in cooling. Now, this is a weird one. Oil immersion cooling was developed by amateurs, was developed by gamers who wanted to overclock their PCs better. So somebody said, well, maybe I'll just immerse the entire PC in a big vat of cooking oil. And it worked. The cooking oil didn't dissolve anything. Nothing horrible happened, but it carries off heat really well. So that was adopted by gamers for their own use, and then it was adopted later by Bitcoin miners. And now it's spreading into data centers. So the thing is, cooling is usually the limiting factor for CPU speed. It's a really big problem. And I mean, you look back at the old days, IBM used to make mainframes in which every chip was cooled by water. They had a pipe going to each chip. Each chip had plumbing attached to it, and they had pipes running to each chip individually, as opposed to just taking the whole damn thing and just immersing it in a vat of cooking oil. So there you go. Sometimes amateurs, beat the pants off the professionals just by thinking of a new approach. All right, so multi-layer static RAM. Now, this is something you may not have heard of. Today's flash memory is multi-layer. Flash memory uses a transistor with an insulated gate. There's actually 2 gates. And at low voltages, you send. I have a question here from Prabir. Okay, so flash memory uses insulated gates, which are field effect transistors are sensitive to electric fields, and the gate supplies the small electric field that controls the current through the main transistor. They use an insulated gate, and they actually have 2 of them. And the reason they use 2 of them is because there's a very thin layer of insulation between them. And at low voltages, you can tunnel between them. Electrons can tunnel between them. Low voltages and low speeds, the electrons have long wavelength. So they can cross over between the gates. So you can charge up the insulated gate with tunneling. You can discharge it by cranking up the voltage on the small gate until it breaks down the insulation, and you get, pardon me, what amounts to an arc discharge. Zzzt. And that eliminates the voltage on the floating gate. Okay, so that's flash memory. Now, chips have multiple layers, conductive layers, that are made out of a material called polysilicon, which is just, it's not, polysilicon means it's polycrystalline silicon, right? It's deposited from a gas, and it doesn't form a nice crystal structure. However, a few years ago, people started making 10 years ago, people started making displays out of polysilicon, and they worked out how to make transistors out of polysilicon. And one of the Asian companies, I still don't know which one it was, decided that they could deposit polysilicon. They already could. It's used for an ordinary conductor in a integrated circuit. And they thought, well, since we can do this, let's try doping it, see if we make a transistor, and it worked. They got it to work well enough to use for storing a bit of data with a flash memory cell. And they so they started stacking them up and getting more and more. And the thing is, it's not, I said it's 192, that's being surpassed now, it's 220 something layers of polysilicon with data stored in each layer. You see, 1 bit per layer. So the result is that flash memory has become much, much cheaper, bigger, cheaper per bit. It's also rather fragile. It only goes, you can only erase each bit about 100 times before the insulator breakdown ruins the transistor. But they have ways of taking care of that, because as it happens, most of the data that you store in a file system never changes anyway, right? There's a lot of it is stuff you're archiving, or it's program code for programs, and stuff like that, which is not going to change every day. It might change very occasionally. And they have ways of distributing the file system around on the chip to equalize the rate at which transistors are used up. Anyway, I think that somebody's going to crack the problem of doing the same thing with static RAM. Static RAM uses transistors switching each other, what's called a latch circuit, and it doesn't require really good transistors. They can be fairly crappy transistors. So since they figured out how to make crappy transistors for flash memory, I think they'll be able to figure out how to make crappy transistors for static RAM. That wouldn't matter if dynamic RAM hadn't got stuck, but it has got stuck. It's not down at 4 nanometers, it's stuck around 10 nanometers. So, you should be able to put static RAM on each level, and you'll have higher density than dynamic RAM. And other advantages. Dynamic RAM has destructive readout. You have to write data back after each read. With static RAM, you don't have to do that. So it's faster. And it takes less power. So on the whole, I think that would be a really great thing. But again, as I said, I don't have any inside knowledge. So I think somebody will solve it, though. Somebody. I wouldn't count on it being an American business, because they already missed out on multi-layer static RAM. It's Asians doing that. So we'll see what happens there. So that's an iffy prediction. It's might be. If it does happen, it'll be great, because it'll mean we can really multiply the amount of RAM that we have. And if we can do that, then we can have a mainframe on a chip, no problem at all. They're a single chip, not just a chip with memory off to the sides. but a single chip with all the RAM on it that we need, which would be amazing. Very nice. Superconductors. Oh, you see, this is, I've got the, I got an out-of-date copy of this. I withdrew that because it wasn't reproducible. So that turned out to be wrong. Okay, the internet was developed in a decentralized manner. Okay, yeah, it sure was. It was developed by a whole bunch of academics, each solving one little problem. And often we ended up in the early days of the internet with some critical part of the internet running on one academic's personal computer in his office.
Yeah.
That's, it's crazy. You think about it now, you go, what? Were you people crazy? Well, nobody knew where it was going. And, it was very much a joint project, though. It was a whole lot of people contributed. The internet has become a venue for waging digital war. Lloyd's of London has announced it will no longer pay off for cyber attacks if the government says the attack was committed by a foreign power. Okay, so there's enough. I mean, it's actual warfare. And Zurich Insurance went further. They warned they and others may leave the cyber attack insurance market entirely. So if your business is dependent on computers, which it certainly is, you should be afraid because you can't get insurance anymore, or you won't be able to. And that means we need to really tighten things up. Right? We need to improve our security architecture. Last year, ransomware gangs started to attack infrastructure businesses. So they're blackmailing, they're not blackmailing, they're extorting money from infrastructure businesses to force them to pay, a fee. Nice business you got here. It'd be a shame if something happened to it. I'll sell you an insurance policy. And that's what's happening now. The US government has reacted by issuing not just guidelines, there are actual requirements for utility companies, because utility companies, like electrical distribution companies, water distribution companies, gas and oil distribution companies, those companies are all heavily regulated. So the relevant government agencies are telling them, you have to do these things. And so far, I have to say, as far as I know, so far, most of the places where they're being attacked, it's basically their own fault. They've left the door open. You got to lock the doors. You don't have accounts that don't have passwords and stuff like that. So that's the first thing. That's the first stage. But that's going to get worse because once they've done that, well, then the ransomware gangs will start attacking in a more sophisticated way. And it's not going to stop until we figure out how to win this war. And of course, one of the entities behind these attacks is North Korea. Apparently, they're making a business out of it. They're supporting their country with extortion across the internet. Again, we could cut them off because we could cut Russia off, and Russia is the only country that supplies internet access to North Korea. So why don't we cut Russia off? Well, we can't. It's too big a country, and we can't cut it off. We committed ourselves. We don't have a way to back out. The US government has also proposed to outlaw the Microsoft-style disclaimer. This software is not suitable for any purpose. Microsoft puts that on all of its software. And it's how they got away with stuff like CBasic, which never worked. And they just said, well, too bad. We never said it worked. Now, other countries already, like civilized countries, have laws that dictate that the seller can't completely misrepresent what they're selling. right? That it has to be fit for purpose. So for example, if I advertise a car that is sold as is, and I sell it to you with the disclaimers as is, and I don't guarantee it works. In the United States, if what I deliver to you is a four-wheeled child's wagon, it's your problem, right? Whereas in other countries, the court will say, well, that's not a car, so it's not fit for purpose, right? So that's going to dismay Microsoft because they rely on that disclaimer. It'll dismay a lot of US companies. And I expect that they'll be, that the disclaimer will only be outlawed for specific types of software, not for consumer goods. Because that's just the way it works in the States. But even if we were doing everything conscientiously, we still don't know how to make correct software. All software has bugs, and by some estimates, it's about 1 bug per 100 lines of code. Newer computer languages try to minimize this, but there's lots of code that we use every day that's older. And specifically, there are 2 languages I'm thinking of, C and C++. When we were putting together the internet, it was all written in C. Later on, there was a fad for C++ in the mid-80s. They're really the worst languages because they're kind of super assembler languages. They allow any code in the program to access any arbitrary memory location belonging to the program. And you can literally, I mean, you can call the random number generator, generate a random number, and then turn that into a pointer and try it, see if it works. That's crazy, right? It's crazy because it's all vulnerable inside a program. There's no internal security barriers inside a program. Even in other languages that are more recent, such as Dalvik and Java, the compiler is still responsible for doing that security. It's not done in the hardware because they don't have it. They have support for it in today's hardware. So I think that's foolish, right? We need to put internal boundaries around objects, I think. And unfortunately, we can't just replace all the old code, even if we had perfect compilers. It took us 40 years to write all the code. And we're not going to be able to replace it in less than 40 years. So I think hardware can help. I think we can do a better job by enhancing hardware to put boundaries around objects. And so I have to discuss tagged architecture. That's something that was abandoned in the 1970s because microcomputers came out and they had very short words. So you couldn't afford to spend 3 extra bits for every 8 bits just to put a tag, right? And that was the implementation in those days. It was every word was tagged. Burroughs was the big practitioner of that. So I've used 3 bits as an example. It could be 4. It just depends. But anyway, you see the difference nowadays. 1960 mainframes had 32-bit words, so tag wasn't too much extra. But then micros came along, and it was a 3-bit word, an 8-bit word, even 16 bits. It was still a lot. Nowadays, we have 64 bits in each word, and a tag really isn't much. 3 extra bits on 24 is only 5%, so that's not too bad. Another problem for tagging in the 70s was the tagging reduces the number of separate instructions. All right. So on an untagged computer, if you want to add an integer to a float, you have to first convert the float to the integer to a float, and then add the two floats. In theory, you could have an instruction that would add an integer to a float, but they don't do that. They say, oh, those are two separate operations, so we'll do it one at a time. The problem with that is that by not tagging them, you made the number of instructions bigger. And at that time, in the 1970s, it was a marketing premise that the more instructions you have, the better you are, right? That was still in the days before RISC, in the days of what's called CISC, complex instruction set computing. So it was bad marketing. But we don't necessarily have to tag data in storage. Now that it's inside objects, we need the object to keep track of what its type is. So then we only need to tag stuff that's in shared, in regions that are shared, regions of memory that are shared, such as the stack, and in general registers, which are also shared by the program. But otherwise, you can rely on objects for typing the data. And I think that's fine. Here's the idea of an object. You have multiple objects that are all the same type, but they all share the same methods. So they all belong to a class, which I've just called X. And the methods for class X is a set of code that's used by every object in class X. There's no other code. There's only the methods for that class. And that means that the object is, it can't go outside the rules set by its own methods. Anyway, so I think we could combine those two, combine objects and class, and get we could get a decent system of memory management. And the reason that's an advantage is that then if somebody manages to take over one object, if they manage to subvert an object because it has a vulnerability in its methods, that only gets some control over that one object, only subverts that one object. So they'd have to find a way to walk from there to another object and take advantage of the vulnerability there, and then from there to another object and take advantage of vulnerability there. And the thing is that in modern computer programs, there are many hundreds of thousands of different classes, never mind individual objects. So, you know, that makes it a lot harder. What if it's written, the program's written in C, it doesn't use objects? That's tricky. You may be able to analyze the source and deduce objects from the source. How to penetrate from one object to another. And that's not easy. Whereas you know, you close the door for one object. And so you can tolerate a lot more bad objects. And so it puts the odds on the side of the defender instead of on the side of the attacker. And that's really the problem. Is right now we're working a form of warfare in which the attacker has all the advantages. So we have to get away from that. Okay, so is that my last slide? I believe that is my last slide.
I disappeared. Maybe it cut out.
Did it cut out? Okay.
Yeah, I dropped out for about 30 seconds. Is everyone still? I mean, I assume everyone's still there. Yeah, still everyone's there.
Can we speak a bit louder, please, Gord?
Sorry?
Yes, okay.
Can you speak a bit louder? I cannot hear properly, Gord, if it's possible.
Okay, I'll lean closer to the mic.
Yeah, that was
been
comment.
I've been working in this area for many, many years, as you and I have chatted briefly. Um, my philosophy is to take a much more fundamental approach based on the changed economics of of hardware. Our idea of using a single processor and running all processes in on a on a time sharing system is based on the economics of 1960s mainframes. Today,
Exactly.
you can actually buy a processor for under $1. An ARM processor, for example, in the Raspberry Pi, is built for approximately $1. So my philosophy is to, and it solves one of the problems you raise at the end, which is the complexity of hardware. A process, imagine a computer where you've got 64, 256, however many processors all sitting running in parallel, each carrying out a dedicated task in parallel with a supervisor that only allows communication between them. You could have a much more robust security system. I think you could have a much more robust operating system other than the, I think, appallingly complex ones we have today and so on. And I think you could, by having each processor running a fairly simple bit of code in order to operate its dedicated processor, say one for word processing, one for spreadsheets, etc., one for internet, I think we could architect a very, very robust computer with amazing performance without really having to invest dramatically in new hardware technologies, but and actually compartmentalize in a physical way the software, which would take out some of the software complexities. I'd welcome your thoughts on that idea.
Well, that's an interesting approach. My my reference point is the large business mainframe, which has to have access to the same data for all of those different applications, and that is an issue. In the end, you're still accessing the same data. I'm not sure that you could benefit as much as what you're suggesting.
I'm not suggesting that they're not interconnected. I'm saying that that's done separately rather than in a shared multi-layered time sharing operating system. In other words, the supervisor would simply be able to communicate data between any of those applications in a much more, I think, a more robust way. Anyway.
Well, it's entirely possible. I mean, I agree that the emphasis on time sharing is really obsolete. You know, no, we're not doing that anymore. We don't have multiple users on the same computer. We have multiple computers for the same user. So, you know, that's silly. You know, it's silly to still have that emphasis. That's the origin of the POSIX security model, which is still the model people use. And I agree, it's a fairly obsolete model. But I'm just looking for a way to patch the mainframe. I'm not really looking for a way to fix the underlying problems. But I mean, there is good work to be done.
I think just to add, Peter, to your architecture that you mentioned, it would separate the errors or any kind of cyber attack. It would bring it down to every element. In other words, if one element runs into problem, it will not impact the other elements. They can carry on. It has this advantage of localizing the attack.
Yeah, and I think it would also make forensics a lot more straightforward, because you would be able to identify where the intrusion had taken place. And anyway, it's let's put it this way: it's out of the box thinking. But I'm simply suggesting, rather than simply try and do what we've been doing for the last 50 or more years in a faster way.
Gord, two small historical points, and then I'll ask the question. I come from India, and I spent 5 years at Imperial College from 62 to 67, where I first learned about computers. And in our high electrical department, there used to be two pictures. One was of Charles Babbage himself, and the other was a picture of a drawing, which was supposed to be a part of the analytical engine. And whether it was or not, I never figured out. The other part is that our our agricultural station was very close to Bletchley Park. And in those days, you could go around Bletchley Park, but you couldn't get in. So for some reason, even in the 60s, it was supposed to be a restricted installation. My question is this. I agree that improvements in hardware are not really where the action is going to be. It's improving the software that has been built around that hardware for the last 50 or 60 years. And I must confess, I'm a software illiterate now. I wasn't when I was actually working on computers 30 or 40 years ago. But are there attempts to look at this problem in a more global point of view? In other words, when I, as a user, interact with my smartphone, with a computer system or a system which consists of computers, telecommunications networks, and the software which glues them together, is the weak point me with my smartphone, or is it in the networking software which runs the system and therefore allows the hackers to make inroads? Because as we know, there's a balance between ease of use and security. And even 50 years ago, when I was working in the computer software industry, the economic incentive is always towards ease of use. Ransomware, I presume, didn't exist at that time. So I'd like you to come back to this issue of what is the best way of fighting ransomware. By the way, the obvious thing to attack is first the electricity grid, and particularly if you go to smart grids, because smart grids require much more computational abilities than the existing Tesla grids. The financial systems, I guess, will protect themselves.
I have to say that smartphones have they actually have a pretty solid architecture to protect you, the user of the smartphone, from the application that you download. So in both the languages that are used, Java is used in some of the smaller granny phones, and now it's Dalvik in the bigger phones with screens. Those are the application is actually represented as code in a machine in which the program can't generate pointers. It can only use them, but it can't generate them. It has to be given pointers by somebody else. That's a very powerful security model. Very powerful. And I actually think it's a good, solid basis for operating. But the trouble is that the applications that are used in business aren't written in either of those languages.
Exactly.
Although some businesses do use Java. When I was at JetForm, we had some customers who were happy for us to give them a Java applet that they could run on their mainframes. So they really didn't want us running a C++ program on the mainframes. They were very reluctant. And so I agree with them totally. You know, I agree with them that that's a good model. It's still dependent on the implementation the software implementation in the essentially the code generator that converts it to local code. That has to be perfect. And unfortunately, about half of all errors are design errors, which we can't find automatically. So there might still be problems that way, but it's certainly much harder to do anything bad on your phone than it would be if they had still tried to just make you write code to run native under. That was one of the problems with BlackBerry, right? It didn't have that model. So it was hard to write an application. Anyway, the bottom line is I think that we're pretty safe going that direction with new code, but the problem is we still have this huge mass of old code that took 40 years to write, and it's just too vulnerable, but we can't replace it. I mean, we can eventually, but it'll take us decades to replace it. So we're stuck, at the moment with, we need something.
Gord, you said 40 years. I bet still there's COBOL E compiler code around.
Probably running some mission critical systems too. Okay, I have a question from Richard Vigar, and I would just like to preamble it. So Richard is asking Gordon if you might comment about the sort of expanding on the evolution on different supercomputer architectures. He's given a web link as well, indicating some choices of what, I guess I haven't checked it out, but choices said a lot of great work on supercomputers. So his question is, can you expand on the supercomputing architectures? As you know, because of, say, large language models, they've been, and also large visual models, they've been using, graphics accelerators as the main processors, as opposed to the older days of specially made chips for high-speed, processing and pipelined architectures like the Cray machine. So the supercomputer is transforming in its architectures today. So I wonder if you could make some comment. This is a question from Richard. And Richard, if you wish to unmute, you can engage with Gordon.
Thank you, Gordon, for the presentation. That's great. Yeah, like there's a lot of movement on the supercomputer front. My background from my earlier work, we had people working on that. I can't really tell you much about that, but I know that there's a lot of companies, there's a lot of research happening in the world, and a lot of it, as Peter is saying, some of it is being driven by large language model and computer vision and the whole world of AI, but without getting into AI, the actual supercomputer architecture is moving in different direction. And I've listened to a conference not too long ago where one of the participants was the BSC, the Barcelona Supercomputer Center, where they were talking about different options, how they were partnering with different groups from around the planet, even on how to move the ball forward on supercomputers. So I was wondering if you had any venture into these sort of architectural aspects. Thank you.
Actually, I don't. My experience is all with commercial computing, which never uses supercomputers. I really don't know.
Okay. Okay. Well, it certainly is an interesting opening field.
Okay, Richard, thank you. I have a question from Edward Atrache.
Okay, the question is there punishment?
Is there a way to discourage hacking by having a suitable level of punishment? It's sort of like if you commit murder, you are hung in the old days. You're caught.
I don't think that's at all possible because, of course, you could be in North Korea doing the hacking, and what are we going to do? Nuke North Korea? It's just not going to happen. someday, when we have a world government. But until then, there's no way.
I mean, in my view, the way to address the suitable punishment is to actually prevent people from having the idea of hacking. So I think what we need is actually more civics, more ethics, and more integrity in our societies. And I mean that globally, is down to the level of the local individual. But that's philosophy. Paybear, your hand is up. Is that a question, or is that up from before?
Actually, a question and a comment on what Ed just said. At the moment, the equation is completely asymmetrical with respect to cybercrime. The cyber criminal faces very minimal punishment and downside, and the gains are enormous. The last time we looked at this problem many years ago in Industry Canada, we'd estimated that cybercrime was maybe a $500 billion industry. So I don't think approaches to morality or civics is going to get you out of this question. And Edward's question remains unanswered. How can we deter hacking?
Trillion transistors on them. And I noted in one of your slides, you commented that Moore's law is dead or it's dying. I'm just wondering, where does this kind of scaling fit into the so-called Moore's law? Because this is dramatic, up to 1 trillion transistors, more than 1 trillion transistors on a little tiny chip. I mean, this is incredible. We're down to that measuring things by a couple of atoms, basically.
Yes, they are. They're not actually as tiny as they used to be. Chips are a lot bigger now, but I mean, they're still not large. Yeah, so Moore's law used to give us higher speed. It doesn't give us higher speed anymore. It used to give us lower power, and you might still get lower power, maybe. Except most of the power now is these signals traveling between circuits. So if you have the same number of bits traveling, you still have the same power dissipation. And what Moore's law gave us was more and more transistors, so we're still getting that.
Yeah, so the higher density allows you to consume less power per transistor, in a sense, because we've got the heating problem. So I mean, thermodynamics is playing its role here. But when you've got 1 trillion transistors versus in the old days 2 or 3 on a chip or a piece of electronic Bakelite or whatever. We're dealing now with more than just the number of chips, the number of transistors, the heat capacity issue, the links between them. We're down talking to now one nanometer wires, this is all scaling, both going up in numbers and down in size. And I would assume because it's going down in size, the performance is going to increase in terms of more efficiency in terms of consumption of power, energy.
Well, the problem is that it's no longer the gates that use the power or make the delay. It's the connections between gates. We've got them so small now that to a transistor, the entire chip is a huge area, and it's a long way to send stuff. It doesn't really work anymore. You can increase the total number of circuits if they're not used very much, like memory, right? With memory, it's only used once in a while because at any given moment, most of the memory is not active. It's just sitting there. So that works okay. You can certainly make bigger memory chips, but bigger logic chips, not so much, because you can't do much with that. It doesn't get faster, and it only produces more heat, but you can't get rid of it. So, and plus we're reaching physical limits. You can't make it, obviously you can't make a circuit smaller than an atom But more than that, you can't even get close to an atom in size because you run into quantum effects. They're already fighting quantum effects at every step. So
why don't we have a little wrap up here in terms of not exactly on what you said, but what you haven't said, in the sense of setting the stage for where we're going and what you've talked about. And that's a little bit about where AI is going. This is something that Greg has suggested. So Greg, maybe you could take the floor.
Thanks, Peter. It'd be great to see some people. I don't know if people are checking their email or having baths and showers in the afternoon, but it's really hard to connect to people when you don't see their faces. I'd just like to just even facilitate a bit of dialogue. Obviously, AI is one of the AI and Fusion were two developments that brought our friend Perry Kincaid out of retirement, doing weekly webinars. Last September, he said, I'm done. He usually wraps up in June, comes back September, came back and said, I'm 80 years old. I'm going to spend time with my grandkids and learn to play the piano. And the Fusion stuff broke October, November. And we've seen what's happened with OpenAI, generative AI, and everything AI. It's, and there's tons of issues. There's tons of societal issues. Some question whether or not we can continue to be human. You know, there's some pretty foundational questions. So I would just, Peter, would you like to give an FSN perspective in terms of what the future program might be? And that
Yes, I will do that. In fact, I think we could just have a general discussion on this at the moment, because there will be a webinar coming up. I will be updating, in fact, a webinar I gave to the very group that Greg is speaking of, Perry Kincaid. I gave an address in mid-February on the rise of ChatGPT and its implications. That is the large language models in general. And that was only the beginning, because things have been going really quite at a lightning speed and at accelerating rates, I should say, accelerating rates in the last few months. So there's a lot to say. I think the biggest thing that's happened about AI is since the beginning of this year is that there is now a lot of talk by governments, both politicians and the senior bureaucrats and those who are in the trenches, as well as by the senior leadership of many AI companies, as well as many engineers behind the scenes in AI companies, that this business needs regulation, and that the regulation needs to come from government. Companies can't stop themselves from doing what they're doing because they're in competition. And so it's hard to enforce, and therefore to create laws, rules, regulations, and guardrails seems to be the trend right now with respect to AI. So I will explore this much further in a summer discussion on the potential for the regulation of AI and the implications of AI as it's now becoming something that the average citizen knows something about in terms of they've heard the term, and they probably fear it like they fear nuclear weapons and biological warfare. So I think there's a great misunderstanding about AI. Natural language processing is only one element of AI, and that's what's dominating right now is the chatbots, as well as the ability to manipulate imagery. So those are only two of the many areas of AI, and so there's a lot to talk about there. So any other comments? I know, Micah, you've got your hand up. I'm sure it's related to what was said by Greg or Gordon. Please go ahead.
Thank you. Yeah, I was going to comment on the issue of keeping data processing secure. And the US patent that I put in the chat was brought to my attention to try to essentially build a hardware implementation of secure data processing systems. It's 2018, and it's essentially based on, reversing von Neumann, right? Not having essentially instructions and data treated the same in memory. It will take a little bit more time to look at this in detail. I have a little spreadsheet, like Excel implemented demonstration of this approach. Be interesting to have a look at that in a bit more detail.
Can I say, I did some work in this a few years back. and actually I proposed an architecture where, this is Peter Chapman, by the way, where, yes, physically separating the executable from the data. And I personally, I think that's such a simple thing to do, and it's key to solving many security issues. But for some strange reason, the computer industry does not seem interested in it. That's my view.
I fully understand, and I've been discussing this with a few folks who are in the industry. So things might change. I don't know. But it's interesting that the US Patent Office went ahead and patented that architecture.
Isn't that what we used to call a Harvard architecture in the old days?
Yes.
It could be, but this is.
So I'd like to thank Gordon for an interesting overview, and some projections into the future of ancient technologies that have been evolved over time, and we're still pushing those limits as we advance. And we've had a bit of discussion around some of those advancements. Maybe we'll address quantum developments in the fall. But for now, we'll stick with the AI story as it evolves. So this was a beginning of our technical side on computing, and as I say, it'll be the next step, and we're going to go down the climate path too. So any other comments, questions, or factoids one wants to raise? Otherwise, I'd call this meeting to adjourn.